Hey everyone, welcome back. Today we're going deep on something super important in machine learning.
Absolutely.
Data normalization.
Yeah, it's a big one.
It really is. And, I think a lot of people kind of gloss over it,
Yeah, they do.
but we're not going to do that.
No.
We're going to get into the nitty-gritty.
All the details.
I've got some really cool research papers to dig into.
Yeah, some good stuff.
One from Mathematics 2022, which gets into how normalization impacts medical diagnoses.
Oh, yeah, that's a really interesting one.
Which is a really complex area.
Really complex. Lots of challenges there.
But before we get into all of that, let's just take a step back.
Okay.
Like, why is normalization even important in the first place? When we're prepping data for machine learning.
Well, imagine you're a machine learning model and you're trying to learn from a data set where some features are like in the hundreds and others are like tiny decimals.
Right.
It's like comparing apples and oranges, or maybe apples and like microscopic bacteria.
Right, yeah, or like, planets and like grains of sand or something.
Exactly. You get the idea.
Yeah, totally. So the model's going to get confused. Right?
Yeah, it's going to get confused and give too much importance to the features with the larger values.
Even if they're not actually that important?
Even if they're not that important, that's why we need normalization.
To level the playing field.
Exactly. It's all about bringing those features onto a level playing field.
I like that.
So the model can focus on the relationships.
Okay, so what happens if we don't normalize? Like, what kind of problems are we going to run into?
Oh, man, all sorts of problems. Your model can go totally off the rails.
Okay.
One of the most common issues is the algorithm might give too much weight to features with larger values.
Even if they're not the most important?
Yeah, even if they're not relevant.
Okay.
It's like a popularity contest where the loudest voice wins, even if it's not saying anything insightful.
Oh, I've been in so many meetings like that.
We all have.
So it sounds like it's not just about accuracy. There are other problems too, right?
You're right. There's a paper called An Investigation on Disparity Response, and they talk about how things can go wrong. They highlight a problem with a method called min-max normalization.
Okay.
It's super sensitive to outlier.
Outliers. Those are those extreme values that are way outside the rest of the data, right?
Exactly. And with min-max normalization, outliers can cause all the other data points to get squished together, leaving these big gaps in your normalized data.
Okay, so it's like if you had...
It's like trying to fit an entire orchestra into a phone booth.
Right, yeah, that's not going to work very well.
Not very harmonious.
No, not at all. Okay, so this makes me wonder, if machine learning models are supposed to be so smart, why can't they just handle data in any format?
Right. Why all this fuss about normalization? It's a good question.
Yeah.
A lot of machine learning algorithms rely on things like distance calculations and gradient descent, which are very sensitive to the scale of your features.
Okay, so it's like if you're trying to measure the distance between two cities,
Yeah.
and you're using miles for one and millimeters for the other.
You're going to get a very strange result.
A totally meaningless result.
Exactly. Machine learning models need a consistent unit of measurement.
To make sense of the data.
Exactly. There's a paper called Effectiveness of Normalization Preprocessing.
Okay.
And they found that normalization helps algorithms learn faster.
Oh, wow. So it's about speed, too.
It's about speed and efficiency.
So normalization is like a productivity booster.
It absolutely is. And it's not as complicated as it sounds.
Okay.
There are lots of different normalization methods.
So it's like having a toolbox with all these different wrenches for different nuts and bolts.
I love that analogy. It's perfect.
Yeah.
The Mathematics 2022 paper lists a bunch of commonly used methods.
Okay.
Like the min-max scalar, the max-ab scalar, robust scalar, standard scalar, vector scalar. They all have their pros and cons.
Okay, so how do we choose? How do we know which one to use? It's like picking a paint color. There's so many options.
Too many options. That's what we'll unpack in the next part of our deep dive.
All right, I am ready to unpack.
Let's do it. Welcome back.
Okay, so let's dive into that normalization toolkit.
All right, let's do it.
You mentioned all these different methods.
Yeah.
Give me the rundown.
Okay, so let's start with one we've talked about already.
Okay.
The min-max scalar.
Right. For our listeners who might not remember from the first part,
Yeah.
remind us how this one works.
Okay, so the min-max scalar takes all the values for a feature
Okay.
and squeezes them into a range between 0 and 1.
Okay.
So think of it like adjusting a volume knob.
Okay.
The quietest sound becomes 0, the loudest becomes 1, and everything else falls in between.
So it's taking data that might be all over the place and kind of forcing it into this neat little box.
Exactly. And one of the nice things about the min-max scalar is that it preserves the relationships between the data points. Oh.
So if one value was originally higher than another, It'll stay that way after scaling.
Okay.
But there's a big but.
Oh,
It's really sensitive to outliers.
right. Those outliers
Yeah.
can really mess things up.
They can really cause problems.
Yeah.
And with the min-max scaler, even a single outlier
Yeah.
can squash all the other data points into this tiny range. And that can mess up your analysis.
Okay, so min-max scaler, simple,
Yeah.
preserves relationships, but
Yeah.
not good if you've got outliers.
Not the best choice for outliers.
Okay, what's next in our toolkit?
Okay, so next up we have the max-ebb scaler,
Okay.
which is kind of like the min-max scaler's more sophisticated cousin.
Ooh, okay, I like it.
Instead of using the minimum and maximum values, it uses the absolute maximum value.
Okay, so if the largest absolute value in a data set is, let's say, 100,
Yeah,
all the other values get divided by 100.
you got it. And that makes sure that all the scaled values
Okay.
fall between -1 and 1.
And it's a bit less sensitive to outliers than the min-max scaler.
Okay, so a slightly more robust option.
Slightly more robust, yeah.
But what if we need even more protection from outliers?
If you need the big guns, we have the robust scaler.
Robust scale.
This is the outlier-busting superhero
I like it.
of normalization methods.
Okay.
So instead of using the mean and standard deviation,
Yeah.
which can be really influenced by outliers,
Right.
it uses the interquartile range.
The IQR.
The IQR,
I
exactly.
remember that from stats class.
Yeah, it's all about the middle 50% of the data.
It ignores those extreme values.
Ignores the extremes.
At the edge.
Exactly. So by focusing on that middle 50%,
Yeah.
the robust scaler can kind of neutralize those outliers
Okay.
and give you a much more stable normalization.
Much more stable. I like it.
Yeah,
Okay, so we've got a range of scalars now
we do.
to handle different levels of outliers.
Uh-huh.
But what about like a go-to all-purpose method?
You want the classic,
Yeah.
the workhorse.
Yeah.
But that would be the standard scaler.
The standard scalar.
It's probably the most commonly used normalization method.
Yeah, that's like the celebrity of normalization.
It is. It's famous for a reason.
It is.
It's based on a very solid statistical principle.
All right.
It standardizes the data to have a mean of 0 and a standard deviation of 1.
Okay, yeah. I remember those terms.
Yeah.
From stats class.
So it's like centering the data around 0
Right.
and then stretching or compressing it.
All right.
So that most of the values fall within 1 standard deviation of the mean.
So it's like creating a standardized unit of measurement.
Exactly. And it works really well for a lot of machine learning algorithms
Okay.
that depend on distance calculations
Oh,
or
sure.
gradient descent.
Right.
Because those methods are most efficient when the features are on a similar scale and centered around 0.
Makes sense.
Yeah.
And unlike some of the other scalars, it doesn't have a fixed range.
That's right.
So if you have new data points that fall outside the range of your original data, they won't get squished.
They won't get artificially limited.
Okay, that's good.
Yeah.
So the standard scalar, versatile,
Very versatile.
good for algorithms that are picky about scale.
Exactly.
But there was one more in our toolkit, right?
Oh, yes. We can't forget about that one.
The vector scalar?
Vector scalar, yes.
What's that all about?
So this one takes a different approach.
Okay.
Instead of scaling each feature individually,
Okay.
it scales each data point as a whole.
Okay.
It treats it as a vector.
Remind me what a vector is again.
Yeah, so in this context,
Yeah.
a vector is basically a way to represent a data point
Right.
that has multiple features.
Okay.
So think of it like a set of coordinates
Okay.
in multidimensional space.
Okay, yeah. It's all coming back to me now.
Good.
So the vector scalar is looking at the overall magnitude
Mm-hmm.
of the data point
Yes.
rather than the individual values of its features.
Exactly. And its goal is to transform each vector so that it has a length of 1, which essentially brings all the data points onto the surface of a sphere.
Okay, so it's normalizing the intensity
The intensity, yes.
of each data point.
Uh-huh.
So I'm guessing this is useful for algorithms that care more about the overall size of the data point
Mm-hmm.
than the specific values of its features.
You got it. And it can also be less sensitive to outliers
Okay.
than some of the other methods that scale the individual features.
But it might lose some information about the relative magnitude
You can, yeah.
of those individual features.
Yeah, it's a trade-off.
Okay, so we've got all these normalization methods.
Well, you do. It's a lot.
It's like a choose-your-own-adventure book
It kind of is.
for data pre-processing.
It is. You have all these different options and paths you can take.
Yeah, and that's why it's so important to really understand them.
Absolutely. You need to know the strengths and weaknesses.
But how do we know where to begin?
Right.
Is there like a secret formula?
I wish there was.
for picking the perfect normalization method?
If only it were that easy. Unfortunately, there's no one-size-fits-all answer.
Okay.
The best choice depends on your data, the algorithm you're using, and what you're trying to achieve.
So it's a bit of an art and a science.
It really is.
Right.
Sometimes the best approach is just to experiment,
Just try different things.
see what works best.
But there are some general guidelines, right?
There are some guidelines we can follow.
Okay, give me the guidelines.
All right. Well, for starters, we can think about how these methods are classified.
Okay.
One way is to group them based on the range of the scaled data.
Okay.
So some of them, like the min-max and max-abs scalars,
Yeah.
they squeeze the data into a specific range,
Okay.
while others, like the standard and robust scalars,
Right.
they don't.
Have a fixed range.
Exactly.
So if we need our data to fall within a certain range,
Yeah,
we'd go with the first group.
makes sense.
But what if we're not restricted by a specific range?
Then we need to think about whether we need to preserve the relationships between features
Okay.
within a data point. All right. So if that's important,
Yeah.
we would probably go with something like the min-max or standard scalar,
Right.
which scale each feature individually.
Individually. Okay.
But if we're more concerned about the overall magnitude of the data point,
Yeah.
then the vector scalar might be a better choice.
Okay, so we're looking at the range.
Yeah.
And whether we're scaling individual features or the whole data point.
Mm-hmm.
What else?
Another important factor is outliers.
Right.
If your data has outliers,
Yeah.
you really want to use a robust method like the robust scalar
Okay.
to neutralize those outliers.
Exactly. You don't want them messing things up.
You don't want them hijacking our analysis.
No.
But choosing the method is just the first step, right?
That's right.
We still have to actually implement it.
That's the next challenge.
Yeah.
And that could be tricky.
Okay.
But don't worry. There are some tips and tricks
Okay, good.
to make it easier.
All right. Well, I think I need a break.
Yeah.
My brain is buzzing.
It's a lot to take in. We'll dive into the practical side of all of this
Yes.
in the next part.
Sounds good.
Okay, so let's get practical. In the last part, we talked about all these different normalization methods.
We did.
But how do they actually work in real-world scenarios?
Well, one of the best ways to learn is by looking at examples.
I like examples.
Me too.
Okay.
Remember that paper we mentioned on proteomics data?
Yeah. Assessing normalization methods in mass spectrometry-based proteome profiling.
That's the one.
It was a pretty dense paper.
It was. A lot of information in there.
Yeah, they were analyzing all these plasma samples to figure out what influences weight loss,
Yeah, and weight maintenance.
weight maintenance.
Right?
It's a complex topic.
It is. What kind of normalization challenges did they run into?
One of the biggest ones was batch effects.
Batch effects. Remind me what those are again?
Yeah, so basically it's when you have variations in the data that are caused by things like differences in how the samples were collected or processed, or even the day they were analyzed. Really, the day.
Yeah, it can be that subtle.
Wow.
Like, imagine if some samples were processed on a Monday and others on a Friday.
Okay.
There might be slight differences in the results just because of the day of the week.
That's wild.
It's weird, but it happens.
So it's like when I bake cookies
Yeah.
and they turn out slightly differently,
Yeah.
even though I use the same recipe.
Exactly. And those batch effects can really mess up your analysis.
So how did they deal with that?
They actually tried a bunch of different normalization methods to see what worked best.
Like what?
They tried quantile normalization, combat, and a method called RUV.
RUV, what's that stand for?
Removing unwanted variation.
Okay, so they were really trying everything.
They were pulling out all the stops.
Yeah. So which one worked best?
Quantile normalization was the winner.
Really?
Yeah, it was really good at smoothing out those batch effects and making the data more consistent.
So it's like it synchronized all the data.
Yeah, like a time machine.
Even though it was collected at different times.
Exactly.
That's really impressive.
It is.
Okay, so normalization is clearly super valuable for researchers.
Absolutely.
But what about the rest of us?
Yeah.
Like, how can normalization help us in everyday machine learning?
Well, let's say you're building a model to predict housing prices.
Okay.
And you've got features like number of bedrooms, square footage, location.
The classic regression problem.
Exactly.
But those features are all on different scales.
Totally different scales. Like the number of bedrooms might be 1 to 5.
Right.
But square footage could be like 500 to 5,000.
Yeah.
So without normalization, your model might give way too much weight to square footage.
It's because the numbers are bigger.
Exactly.
So it's like those features are all talking at different volumes.
Yeah.
And the model can't hear them properly.
Exactly. Normalization helps to balance things out.
So everyone has an equal voice.
Everyone gets heard.
Okay, what about another example?
Sure. Let's say you're working with online reviews.
Okay.
And you want to analyze them.
To see if people are feeling positive or negative.
Exactly. Sentiment analysis.
Sentiment analysis.
So one of the first steps is to count how many times different words appear.
Okay.
But longer reviews are naturally going to have higher word counts.
Yeah.
Even if they're expressing the same level of sentiment.
So it's like they're shouting their opinion.
They're very enthusiastic.
While the shorter reviews are whispering.
Yeah, they're a little more subdued.
But normalization can help adjust for those differences.
So you're comparing apples to apples?
I'm starting to see that normalization is like a universal translator.
I like that.
It's breaking down the barriers.
Removing the obstacles.
So machine learning models can understand.
It makes the data clear.
But it's not always the answer, right?
You're right.
There are times when we might not want to normalize.
Sometimes the raw values are important.
Okay. Give me an example.
Okay, so imagine you're working with financial data.
Like stock prices.
Exactly. The actual dollar amounts matter there.
Right. A $10 change means something different.
Yeah.
If a stock is at $10 versus $100.
You don't want to lose that context.
So normalizing that data would be like
Yeah.
converting currencies without the exchange rate.
You'd lose important information.
And normalization can also make it harder to interpret the results.
That's true.
It's like we're gaining clarity for the model,
Mm-hmm.
but maybe losing some of our own understanding.
That's a trade-off.
Okay, so normalization.
Yeah.
Powerful tool,
Very powerful.
but use it wisely.
Wield it with care.
Well, I think we've covered a lot of ground today.
We have.
We explored why normalization is important,
Yeah.
what methods are available,
We have.
how to choose the right one.
And even some of the potential pitfalls.
So hopefully our listeners are feeling a bit more confident
I hope so.
about tackling their own normalization challenges.
Yeah, go forth and normalize.
Thanks for joining us on this deep dive into the world of data normalization.
It's been fun.
We'll catch you next time for another adventure in machine learning.
See you then.